derecha.
Hello and welcome to the Advanced Structural Steel Modeling webinar for CivilFEM 2016. In this webinar we are going to talk about the structural features of structural steel modeling features of CivilFEM. I'm Javier Marcelo and here with me is my colleague Román Martín, and he's going to be responsible for the presentation. But before we start, I'd like to introduce the options you have to contact with us using the social media networks. You can reach us using Twitter with our account at CivilFEM, and we are going to use today the hashtag CivilFEM2016. So if you want to comment anything about the webinar, you can tweet anything to us, and we'll be glad to answer that. And after the webinar is finished, we are going to upload the video of the webinar in our YouTube channel. CivilFEM, the channel is named CivilFEM, and here you can find several cases and past webinars for you to enjoy. And so without further ado, we are going to start the webinar. So, Román.
Hi, good afternoon, good morning. Well, let's start with the webinar. This webinar is about advanced structural steel modeling in CivilFEM 2016. Well, steel and steel sections, non-linearities are very important in this sort of structures due to material and non-linearity behavior, and also geometrical non-linearities, large second-order effects, and also the effects of different connections between beams and voided connections that can have a flexible union and stress distribution. Well, in order to design our structures, taking into account all this the steel behavior, we can follow different structural steel design codes. CivilFEM has many we can use to check and design. And well, all the codes requires the consideration of second-order effects, especially for slender sections, and also they reduce mechanical properties due to the possibility of local buckling in different plates of the sections. So while codes allows linear combinations of loads to analyze a lot of combinations, different combinations, check by code, taking into account second-order effects and property reductions. And well, in other cases, for compact sections, the behavior is the opposite. They don't suffer local buckling, and moreover can develop plastic hinges, and this formation of plastic hinges can redistribute forces and moments. So well, it makes sense to perform a nonlinear plastic design. But we can also solve linear elastic models, take into account this possible stress distribution, forces and moments distribution, and check by code, make a verification by code. In this webinar, we are going to perform both sorts of analysis, performing linear and nonlinear analysis of steel structures, calculating load carrying capacity, global structural buckling and local buckling, different models, and of course safety according to structural steel design codes. As I said before, we can perform linear and nonlinear analysis. The advantage of linear analysis is that the relationships between the loads and displacements, there's a linear relationship, so solution is fast and direct, and we don't need high computer codes due to iterations and load incrementations. Also, it's allowed to make linear analysis, allow superposition of loads, and to perform load combinations, and then check and design by codes. But the advantage of nonlinear analysis is that with a nonlinear analysis you can obtain the equilibrium path. The equilibrium path is the real equilibrium path is the relationship between the applied load and the displacement or any other type of sort of result strains in the model. that is naturally nonlinear. This can be used for stability analysis, local and global backlink, forming a detailed analysis, and with introducing the model nonlinearities as large deflections, material nonlinear behavior of steel. Also for reserve strength analysis to calculate the load carrying capacity and what happens if we have loads over the design loads. Progressive failure analysis, like a pushover, crack propagations. Also, this nonlinear analysis can be used for research, understanding the behavior of the structure, performing these simulations, and establishing analysis and design method testings. And well, moreover, not only in these cases, but also it could be much easier to perform a nonlinear analysis involving all this behavior. Performing, for example, a nonlinear backlink analysis could be easier than performing the linear solution and then calculating section reduction properties and so on. With CivilFEM, you can perform both analysis and increase the quality of your designs. In order to see these CivilFEM capabilities, we are going to perform or to see two different models, building and a steel frame. This building we will perform a design by code and also some details on linear analysis. And for a steel frame, we will perform a full nonlinear backlink analysis, taking into account also stiffener plates and a very detailed model. For the steel building, we're going to start making linear analysis with static and responsive spectrum analysis, combining them and designing by code, checking by code the model. And we will see after this connections models and a pushover analysis. Okay, well, here I have the model I have previously loaded. It's a simple model. If I hit all the geometry, it's geometry done with some loops that would generate lines and then mesh those lines with steel beam sections and also some concrete slabs. In this case, we are not analyzing the concrete slabs. Here in the model, we've defined different load combinations. An important part of CivilFEM is that it is object-oriented. That is, we work with structural objects, structural elements, not with finite elements. So, in example, for defining these columns, I just create a line, and when meshing that line, I will create with the whole line a structural element. In this case, this column is, I've named it with C1A1. Automatically, when meshing it, CivilFEM will define the code properties. Here you can see CivilFEM calculate the lengths, and well, there are some coefficients like the connection coefficients that should be modified by the user. Also here we have other data, that is the unbraced length. If we need to calculate the different bracings we have to add to a column to avoid buckling, we can perform different check-ins, taking into account different possibilities of this braced length and improve, make our designs. Well, the way to apply loads is also based on these structural elements. An example, other structural element is this slab. I can apply an overload over this slab very easy. Here in loads, define like groups. So well, in this overload, I can give a name. And here inside this overloads, I can define a punctual single or a line load or surface load. I can define a surface load, so it's very easy clicking where. In my structural element is 1, define the direction, -1, and give a value to this pressure. And then, well, clicking here OK, I will add a pressure here. It's very easy to define loads and then to combine them. The loads I have, we can plot them. Different load groups is overloads here. I'm plotting them on the mesh. Sorry, here use overload. Here I have these overloads. I also have wing loads, lateral wing loads, columns, and I have also gravity and a spectrum. The way to perform a spectrum analysis plus static analysis is defining the spectrum in the same way we did with that pressure. So I will have here on my right the entities of the model, the Eurocode. A Eurocode spectrum of the zone that we have this building. If I click here, the properties are seen here on the left. We can see here we have also to define the number of modes to extract. We can extract higher number of modes, also combinations we are using, and spectrum direction. We can apply to different directions. If I would like to apply spectrum to 3 different directions, I should define 3 different spectra with different directions. Well, after defining my loads, here in my load codes, I have the different combinations. Self-weight with a coefficient 1.35 plus overloads plus seismic. These other combinations is the overload plus wind and wind with different coefficients. If I click on any of them, here I can see that is the group of loads I'm using on every combination. Now the way is just pressing start here for solving the model, and CivilFEM will solve all the combinations. I'm not solving the model because I don't want to spend a lot of time solving models, but I'm going to load the solution I have here. In results, I'm going to load, in example, the seismic combination. The name of the result file is exactly the same I have here, so it's very easy to identify which result file I need to load. In this case, I'm going to load this combination. Okay, for this combination, let's clear first the loads. I can plot forces and moments, any type of sort of result. So here, result, I'm going to play an example, bending moment around Z axis on beams. I have 2 ways to plot these results. One, the thickness here, and the other way is using the typical diagram. Also here we can see. Well, I can see the maximum bending moments are on the connections between beam and columns. Also, if I plot axial forces, I can see that here the stiffness I'm using for lateral loads, here these crosses will have some axial forces, some high axial forces. Well, after reviewing forces and moments, I can perform a design by code, check by code in this case. I'm going to check beams and columns. Here, clicking here, I'm going to check that combination. So the name, the default name that CivilFEM will use for this combination, here you can see is the same name, but at the end it's added the combination type we are using. CivilFEM has different combination types that are defined in codes and standards. In this case, the code I'm using is defined at the beginning, environment. In this case, I'm using this structural steel code, but well, we have a long list of structural codes we can use. Well, the checking type I'm using is bending plus axial plus shear and torsion, to take into account all these forces at the same time. And clicking here, we will perform a CivilFEM will perform a checking type. It takes just a few seconds, and we can load those results. Here in the results again, load file. We have 2 different sort of result files we can load. The normal result files we have previously loaded, and also checking and design result files, that the extension is different. If I modify it, this is the checking and design result. I open it. And well, the results we have is total criterion. Total criterion is the ratio between demand and capacity. So if this ratio is greater than 1, the model is, the elements are not okay. And if this ratio is less than 1, sections are okay. And also CivilFEM calculates some other intermediate values like flexural dorsal buckling, flexural, shear stress, normal stress, well, section class, slender, not slender. Calculate some intermediate values that are needed to calculate capacity of the sections. You can also plot it. Here to see, to plot, instead of plotting all the model, I'm going to select only beams and columns. So if I go to the structural elements, I can find them here, but also clicking here, the structural elements. I have here a classification of the structural elements. You can see here by default group and the stiffeners. In the default group, I have all the model and the stiffeners are those crosses. I'm going to unselect all the stiffeners. Well, in my I'm going to organize them by name and unselect all the stiffeners and also the different slabs, concrete slabs. So I unselect them, and here I have the model only beam and columns. So let's plot results, total criterion. I can see that this total criterion is greater than 1.85 in the worst points of the structure. In order to see them easier, the points it's not okay, we can change the range of plottings from 1 to 1.85, which is the sections that are not okay. Here we can see where the colors plot that this is not okay. These points are mainly in the connections. Well, we can analyze in detail those connections to improve my model, but we know that is the most complex point of my structure. Let's see a detailed model we've prepared of those connections. I don't save the model, and here in connections we've done two different models, two different configurations. Here is one configuration. It is a bolt connection. It is a mesh with solid elements. We have also added some bolts here, and here the connection plate. And well, if we see the material, now this is a nonlinear model, and we are using this behavior, this bilinear behavior of the steel with a horizontal branch. And well, there are two different values for different steel thickness. We have also different contacts between the different parts of the model. The way to define contacts in CivilFEM is very, very easy. It's here on the mesh. Pressing this button, contact, we select the contacted and contacting structural element. So first here we can select this plate. Well, in this case the contacted will be the column, and here in this other case will be this one. So just clicking OK, the contact is completely defined. I don't need to define anything else. Just the only thing is define the contact behavior. It can be glue, that is a glue, continuously glue, so it could be good for a non-continuous mesh that I need to glue different parts of, or frictional contact. This frictional contact, I define the properties that is friction and also a maximum shear stress on the contact. In this way, I can define all the contacts between my model, between bolts, beams, and so on. And well, we apply a bending moment in this part. The way we apply bending moment is in this area, apply a pressure with a gradient. We can see in the loads the bending moment. Here you can see we have applied a pressure on my model with a gradient that is defined here. So with this slope, and I solve the model with a nonlinear analysis. Here in solution, I add large deflections to take into account second order effects, and also the step of this model is 0.01. Time at the end of the solution is 1 second, so it will be divided into 100 steps. Just clicking here, it starts solving, and I get the solution. If it stop converging in a previous load step, I will know the percent of the load I can add here. Let's see the results. Here we have all the solution, and it has finished in the step 87. I know then that this connection, the failure of this connection is when it reaches the 87% of the loads I've applied. I've applied a very high bending moment, so until it collapses. Let's see results here for this load. Let's see first vertical displacement, set displacement. Well, here you can see that there's a separation here due to this strains in the bolts, and well, there's a small part in contact here on bottom, and also there's a bending on the column due to this deformed shape. Let's analyze yielding. I can see the yielding in example plotting equivalent plastic strain. Plot it, and I can see most of my strains are concentrated in my bolts. They have the highest plastic strains here, but in order to appreciate all other zones where yielding is happening, I'm going to modify the range and also the scale, 4 times scaling it, and also I'm going to reduce this range well. Here I can see I'm having a lot of yielding zones in the web of my column, also here in the point of compression, and also here in this part of tension. Well, also to get my capacity curve of this model, I click results, and I'm going to plot in example vertical displacement of one of these nodes versus time or versus loads. The way to know which node is this, in example, I can activate graphic selection of nodes, and I can see here if this node is, well, here I can write a number. If I graph the results, I modify again to I deactivate the graphical selection of nodes, and I'm going to plot the path of this vertical displacement versus loads. So I can plot it here. I can add, well, I have to select vertical displacement, set, and here type the previous number of the node I've seen, and press OK. So well, this is my capacity curve of my model. And well, I would like to take other configurations. I'm going to add here some stiffeners, some stiffener plates here and here to improve the column, and also here other triangular plate stiffener to improve this yielding part. If I load that model, and well, I also apply here vertical load, well, bending moment, and also I'm going to plot similar results. After applying the load, I applied in this case a higher load. The final solution was obtained for the 85% of the loads I've applied. I open it, and I'm going to plot the same way, vertical displacement. I'm going to increase the scale to appreciate it. And well, here is the vertical displacement. And we can see here also my unfavorable point of this are these bolts. Well, here I'm going to plot yielding as I did previously, equivalent plastic strain. And well, I can see most of the plastic strain on my bolts, and well, I also have some here. I can reduce also the range a little bit, and well, I can see the most unfavorable points now are here on the web of my column, and also these bolts. If needed, I could improve my bolts, having a better steel, and also add any diagonal here in my column. And also plotting vertical displacement versus loads, I can get the capacity of this connection. Also, I can plot the angle, the rotational angle of some of these nodes versus loads. But in my case, I'm going to plot displacement versus load of the same node I did previously. It has the same number. And well, here I have the solution. You can see at the beginning it's more flat, and then the collapse happens like more suddenly. If we compare both loads that we have, both models we have obtained previously, we have solved previously, we can see here the animation of both without the stiffener plates on the left and with stiffener plates on the right. We can see the format shape is higher on the left. Here it starts later, and yielding starts later, and well, the collapse is more suddenly. If we plot both curves together, here we can see one of them, and this is the other. This curve can be used for this sort of curves that we obtain from nonlinear analysis, can be used for a pushover analysis. This is a plot of a pushover analysis. We compare capacity and demand curve, and we can see very easy that in some situations, with this union with higher stiffener just could come to the higher demand, a point to a higher demand, and a structure response, a structure behavior could be worse than flexible unions, stress distribution, higher displacements, but just carrying the demand curve to the capacity curve in the elastic branch of this capacity model. So well, this can be used for increasing the ductility of the model and just analyzing higher loads over my design loads. Also, here with this connection behavior, we can add this connection behavior to the whole model. If I go again to the global building, here between my columns, I can very easily define between the column node and the bin nodes. I can define nonlinear springs. They can be defined here: mesh, springs, nodal springs. They can be rotational, linear springs, surface. Well, there are different options. We can define a nodal springs between one node and the other node, and then with this node, these springs, we can define the behavior we have, the nonlinear behavior we have obtained in the previous models, detailed models of the connections, and we can use those springs plus in the material structural steel also adding the behavior, the analysis, nonlinear behavior by linear behavior here, and we can perform a nonlinear analysis on the whole model, a pushover analysis. Here we have increased lateral loads in the pushover analysis. Also, we have added the pressure on the different surfaces. They can be transformed into masses, dead loads. Clicking here, we convert them into masses automatically on different slabs. So it's very easy to convert pressures and a linear elastic model into a nonlinear plastic model, adding masses and performing a pushover analysis. If we see the results here of this pushover analysis, we are plotting here displacement versus loads, and here we are plotting plastic yielding. We can analyze now where the failure happens, these columns, and now failure doesn't happen on my connections. Well, next example we are going to see is a full nonlinear backlink analysis. We are going to perform this full nonlinear backlink analysis on a steel frame. The way to perform this full nonlinear is performing first a linear backlink analysis, obtaining the backlink modes. And with these backlink modes, we will use like a starting point for the nonlinear analysis. We need to apply initial deformity shape that will be used like as eccentricity for the detailed model for a backlink to occur. If the model is completely symmetric with symmetric loads, the backlink could not happen. And also we are adding geometric and material nonlinearities for having plasticity and also second order effects on the model. Well, let's see this model. Let's load this model. Well, first here for the backlink analysis, I've defined two different combinations, snow and wind. The difference between these combinations is that the snow is the highest combination with vertical loads on the model. There are symmetric loads and pressure over all my model. If we plot those loads, here you can see the pressure plus self-weight, dead loads, and some other loads. But I've also generated the wind combinations that the lateral wind will create lateral pressures on both sides, also a vertical pressure here on one part of the roof and suction on the other. So if we plot it, we can see a wind pressure here that is vertical and wind pressure in the other part that will be in the other direction. The way to analyze these both combinations is because I would like to obtain symmetric and non-symmetric backlink analysis to analyze both. That is backlink analysis, lateral analysis, backlink, or other sort of backlink, and maybe there's any asymmetric mode that we need to analyze. After generating these modes, these combinations, I solve the model with the linear backlink analysis. Just clicking start here, we will obtain the modes. The way to define with how many modes I would like to obtain is here, and setting here the number of modes. Here the number of modes in this case is 13. And press OK and solve the model. So I've previously done it, and if I see my results, here I'm going to open both combinations. I can see here in my working folder I have 13 combinations for the 13 modes for the snow combination and 13 for the wind combination. Let's plot these backlink modes, clear loads, and let's plot displacements. If I analyze this, well, here we can see the scale is very high, 4,000, but it's easier to see. We can see this is local, mainly local backlink of the web, but also on the top flank there's small backlink, but it's not a global backlink of the structure. I can advance from one to the next one, and I can see most of these backlink modes are a local backlink, that's a backlink of the web. If I advance until backlink mode 28, here I can see this is the first mode I get. I'm going to reduce the scale a little bit. I can see this is the first global mode I am having. This is lateral backlink on the mode. So well, I'm interested in seeing both modes in the nonlinear analysis to introduce both deformed shapes to reproduce this nonlinear backlink, and then introducing this deformed shape, analyze which is my current load of the model and when shading starts, and a detailed safety factor of this structure to analyze when collapse happens and so on. So well, the way to do that is creating other model. Well, I didn't explain before, to perform a backlink analysis is when starting the software, new analysis. Here we have to select 3D static backlink analysis, structural. If we are not solving the backlink analysis, now we will solve the nonlinear using these mode shapes, these backlink shapes. I'm going to open the next model. I've solved here 3 different models with different deformed shapes. Let's see the first one. This is my first one. This is exactly the same model I have, but I've changed the material behavior. Material behavior now for the analysis is bilinear, and also I'm solving a static with large deflections, large displacements. So I will take into account second order effect. And the next step I have to do is to apply a small deformed shape similar to the first mode, that was local backlink of the web, and also the global lateral backlink of my model. So first I'm going to use the first mode. Here clicking, I'm going to apply a deformed shape. So I have to read, to apply this deformed shape, the results of the mode. The first mode is here, and this is the deformed shape I'm going to apply. I can apply it in two different ways. Applying a scale factor to the whole results, the whole displacement I obtained in the result file, or I can scale it to a maximum displacement. I'm going to do it and scale it to 5 millimeters. Well, now I'm going to scale it to a higher number first, to 100 millimeters, just for you to be able to see the deformity shape. Here you can see I'm added a small deformity shape, so when applying loads in the plane of the web, I'm adding some eccentricities that will generate this backlink mode. So now, applying the loads and solving the model, I'm going to obtain the deformity shape of the model. Sorry, in results. And now I'm going to plot horizontal displacement. In this case, I did the same of the previous nonlinear analysis, applying the loads, increasing those loads by a factor, and solve the model with a nonlinear analysis. And so the solution at the end of the solution finished when I have the 85, sorry, here first mode, when I have the 93% of the load. So with the 93% of the load, I have the maximum load carrying capacity of my model. If I plot horizontal displacement, well, I can see that even if I applied an initial deformity shape similar to the first mode, local backlink of the webs, if I plot the result I obtain, my backlink mode I'm obtaining is similar to the global one. So even if trying to reproduce the first linear backlink mode, I couldn't do it adding a high deformity shape because, well, the most unfavorable for the nonlinear analysis, the most unfavorable is the lateral backlink. It is reproduced first with the nonlinear analysis. I will do the same, but applying the initial deformity shape of the 28 mode, that is the lateral backlink. Lateral backlink, and I open it. So, well, it's exactly the same nonlinear model, but now what I've done is in the mesh, I've modified the deformity shape, and I'm going to add the deformity shape of the lateral backlink. I follow the same steps, but now I'm reading the number 28. The number 28 is the we'll see here. I'm going to scale it. I'm going to do the same that in the previous step, increase it by a high number for you to be able to see it. And well, here you can see I'm introducing, I don't know if you're able to see it, I'm introducing just a small deformity shape on the mesh that will induce this lateral backlink. So, well, if I read results of my model, here, let's say, if I see results of my model, after applying the load, I can see the last load step that is solved is the number 85. So I have 85% of my loads, which is smaller than with the first mode, that it reached 93%. So with this, see, I'm going to plot in value, displacement, and well, deformity plus undeformity, and here I can see this is the deformity shape of my model, the lateral backlink. I also can plot where yielding is happening, and I can improve my model, adding some stiffeners or designing in other ways. Well, you've seen previously Well, here this warning error is that say I've solved the model with I've solved the model with a different model. That please check the model carefully. This message is due that I've modified the mesh a couple of times, the deformed shape. So the software realized I've modified the deformed shape. So it's saying that results is not done with this initial deformed shape. That is the reason of this. And we see we are getting some yielding in some points. Well, in the same way we did. Well, if we see the animation of this model, we can see how this backlink is happening. And well, we see we've added an initial deformed shape at the beginning. This initial deformed shape, this maximum one that I added 5 millimeters, that's the model how it was solved. That is defined by different codes and standards. But well, for having a much clearer structural behavior, we can solve the model a couple of times with different initial deformed shape, scale it to different values, and compare both data. These are the results. Displacement versus horizontal displacement versus loads. Well, loads here in bottom and displacement here on top. And I added a centricity of 1 millimeter, that is the higher line, 5 and 10 millimeters. We can see with 10 millimeters, just backlink start happening before, just the horizontal deformed shape start before. But at the end, when collapse happen, well, it happens with a similar deformed shape. Well, so you can see we can combine linear elastic behavior with different models, check by code for initial configuration of the structure, and then perform a nonlinear daily data analysis to get much more information about the behavior of our structure. All these analysis types can be done with CivilFEM. Faster linear analysis, load combinations, cover much more cases, and obtain an initial design of the structure that after checking and design by code, and then have a much more accuracy results performing nonlinear analysis, nonlinear verifications of my previous designs. That can be done for all sorts of steel structures. So, well, the applications of advanced steel modeling for seeing CivilFEM, it's very big. Any structural steel model, because you can model any sort of, you can use cells, solid or beams to model any sort of steel structure, designed by code and standards, and also go further with nonlinear analysis, calculating the equilibrium path, those capacity lines we did, to perform stability analysis, obtaining local and global backlink, also know the reserve strengths we have, that is the reserve capacity of the sections, and what can it happen when loads over the design loads, the loads are used to design the model. This can also the software can also be used for progressive failure analysis, pushover, health monitoring, also in research, and also for reliability analysis to know all the behavior of the structure and their serviceability loads. And well, the advanced steel modeling with CivilFEM allows us to understand the real behavior of the structure and what is most important, to obtain the real safety factor and the real behavior that we are going to have, and avoid collapse due to suddenly overloads, and of course optimizing our structure, improving the design in the weak points, and well, reducing sections where they are not needed. Well, as we have seen, CivilFEM lowers the barrier of nonlinear analysis, and we're combining this with a very friendly, easy-to-use graphic interface. We can solve a very big variety of problems, linear and nonlinear, with single and multiple nonlinearities. If you would like to contact us for further information, for checking the software, you can contact here in this to some of these emails, and also going to the website. If I load the website here, the website. It's CivilFEM.com. Here you can get the information about your nearest CivilFEM distributor. Clicking here, and here you have the world map with the nearest distribution, the local distributor, or you can contact them. And also for next webinars, you can here at CivilFEM webinars, and well, see next webinars. The next one will be in 1 month. It will be dynamic analysis with CivilFEM. So well, okay, save the date. And well, thank you very much for your attention. You can send us your questions using the Twitter account, and well, by email or as you decide. Thank you very much. Bye.